So welcome everybody to this week's Oxford Discrete Maths and Probability Seminar. It's a huge pleasure to have Mariana Olvera-Cravioto, who's speaking to us from UNC Chapel Hill, or rather from her home. She's going to speak to us about PageRank on directed preferential attachment graphs. Thanks so much for joining us, Mariana, and over to you.
Well, thank you, Christina, for the invitation. It's a pleasure for me to be here. And I came to tell you a little bit about one of my favorite topics lately. I love graphs. I love heavy tails. And one thing that I love probably more than both of them is finding heavy tails in graphs where you don't expect them. So that's a little bit of what this story today is going to be about. And this is joint work with my colleague, Sayam Banerjee, here also at UNC, and our current student, joint student, Pravanka Deka. So this has been quite an interesting adventure. Let me just start from the beginning so that nobody gets lost. What we consider here is a directed multigraph. So I'm going to call this standard graph G with a set of vertices Vn and a set of directed edges En. And this is going to be a multigraph. We're going to allow multiple edges that go into the same direction between two nodes and potentially some self-loops as well. We're going to construct the sequence of graphs by adding one vertex at a time. So on each time step, somebody comes in and is going to be assigned a certain number of outbound edges. So the nth vertex to come in gets sample from some place. I'll explain later that it's usually convenient to assume that they're coming from some IID sequence and out degree. And this is going to be a number of outbound edges. And then this person is going to decide who to toss those outbound edges to, according to some random rule. I'll talk about a couple of different models in which we can do that. So I'll leave it for now on the just random way of choosing who to attach to. And we're going to define, in order to define this attachment function, the total degree of the vertices that are there. So this is the total degree of vertex I at the time that the nth vertex comes in. So n minus 1 vertices have already fully attached, and I'm attaching the kth of the outbound edges of vertex of the new incoming vertex n, and I'm going to decide who to attach it to, and the probability that I'm going to attach it to is going to be a function of this degree of each vertex I at that time. At the beginning, because everybody gets assigned their out degree as they come in, then when a new vertex comes in and I haven't attached any of their edges, they start with an initial degree or initial total degree of dn plus, right? So this is the standard sort of setup for any kind of general attachment graph. In this particular talk, I'm going to focus on just one case. The more general setting is also there, but just for the purpose of showing you these weird heavy tails, I'm going to stick to linear attachment functions. So this is going to cover the two main cases that we're used to seeing in the literature. In general, all we need to assume is that the attachment function is always positive for any value. And remember, anybody comes in, by default, they get an out degree. And I'm assuming that the support of the out degree distribution starts at 1. So we don't end up with isolated vertices anywhere. And in general, this vertex n, when it comes in and is trying to attach its kth edge, outbound edge, is going to do so proportionally to that function f of the total degree of each vertex. So if we think about this a being positive, like in a linear preferential attachment graph, then you know that vertices that already have a lot of neighbors are more popular, and therefore they're more likely to get new incoming vertices attached to them. The opposite end is when everybody gets the same sort of value, only uniform attachment, in which case I don't care who I come in, I choose uniformly at random from anybody, so everybody gets the same chance of getting a new incoming neighbor. Now, these models have been studied. These are nothing new, and normally they are studied in the case of uniform or sort of finite out degree. Usually it's denoted M if you look at most of the literature out there. Here I'm going to allow the out degrees to be random. And again, I'll talk a little bit more about what is the way in which we choose the out degrees, but for now you can think of this as some deterministic sequence coming from some choice that we're going to do. Now, one thing to observe in the directed case, this is not exactly the most interesting real world graph is because it has no directed cycles. There's no reciprocity, right? So everybody comes in and I always attach to somebody who's already there. So there is some timestamp structure that does not allow me to have directed cycles. Nobody older who was there is going to come back and say, hey, it's worth pointing to you. So now I'm going to talk a bit about local weak limits on these graphs. And for that, I need to first explain how do we do an exploration of a directed graph like the one I just described. I'm going to call GIK to be the exploration, the subgraph of my big graph that results from exploring the in component of vertex I. And I'm going to do so breadth first by looking at exactly K steps or K hops away. So this is the in component of depth K started at I. And you would say, well, as you're going in and looking at the in component, I'm looking who's connecting to me, then who's connecting to those people, who's connecting to those in that order. I'm also going to be discovering other things as we go. In particular, I'll be discovering perhaps how many outbound links they have. And what I'm going to do with those is I'm going to attach those to my exploration as a mark. So this out degrees, they don't get used to define the graph structure of the in component. They just get attached to each vertex as some vertex attribute that we will use later to do other things. We'll be talking about random walks. So we're going to definitely need these guys, but they're not part of the edges. They're just a mark on each vertex. Now, I do like studying PageRank. In general, I tend to study PageRank when we have the more general setting called personalized PageRank, in which case it's not only the out degrees that you need, you also need sometimes something called the personalization parameter or teleportation probability. So I'm used to thinking about vertex marks, not just as the out degree, but some other vertex attributes that you can toss in. In my mind, for the analysis of PageRank, this usually includes the out degree, but also this personalization value. Now, for the purpose of this talk, the personalization value does not play an important role, so we can keep in our minds that we're just looking at the out degree as a mark. However, in the general setup, the marks can be whatever I want them. And for other more interesting problems outside of PageRank, sometimes it comes in handy to make them quite general. So this is my notation for the marked in component of vertex I of depth K. So I start at I, this is the graph structure, this is the depth of that component, and this just denotes a generic mark. It's not referring to any particular value, just the type of the marks. Now, I need to define a few things so I can talk about what kind of limits we look at. The first thing is I need to define my graph isomorphism in between two multigraph, directed multigraphs. And in the multigraph setting, we need to not only keep track of who those are the vertex correspondents, but also the number or the multiplicity of the edges, right? So if I have two edges going from vertex 7 to vertex 17, there must be a bijection sigma that allows me to map the 7 and the 13 sum of the vertices on the other graph, and they need to have the same multiplicity. So this is my notation for the number of self loops of each vertex and the number of edges from I to J, and then we have to have correspondence between the two. My notation for the graph isomorphism is just this wiggly term here. Now, because the marks are there, and the marks, as I said, we can think of them as coming as from some random distribution themselves, sometimes ID, sometimes not quite ID. And again, this comes from applications where you want them to be a little bit less than independent. In that case, I'm going to work on this probability space, which I denote the probability space conditioned on the marks. So now the marks become deterministic under these. I will take a limit later to take care of that. And again, the main thing, it's not for this talk in particular, but that those personalization values and in other recursions that I like to study, usually they're not quite independent. They're just asymptotically independent. That's the need for having this sort of conditioning step. So I'm going to define now something that I like to call a strong coupling. And that a strong coupling basically says I can construct my exploration of the graph started at a uniformly chosen vertex IN, and I can construct a limiting graph such that they're constructed both on the same probability space, and that once I look at their graph structure, they are isomorphic to each other with high probability under these sort of conditional space given the marks, right? So this is just my standard notion. This is not quite the local weak convergence or local weak convergence probability. It implies local weak convergence. It does not imply the other one. I'll get to that in a second. But you can see the good thing about having this kind of coupling usually is that once they're constructed in the same space, you can do a lot of manipulations inside the probabilities. And because these are mark graphs after all, then I'm gonna also add the mark structure. If the marks are discrete, this doesn't quite need to be the way it is. But if the marks are not discrete, they're continuous value, let's say those percentage values, then the best that I can do is I can guarantee that the distance between those marks, this row is the distance on the space of the marks, are uniformly smaller than some epsilon for any fixed epsilon. Again, if the marks are discrete, let's say just the out degrees, which take values 1, 2, 3, etc., then I can take epsilon to be 0 and all is good. But when they're not discrete, this is the best I can do. Notice that this sigma is the isomorphism that is defined by this part of the event, which we assume it's there. So this is what we call a strong coupling. And as I said, it comes in quite handy for doing lots of manipulations. Now, if you're more used to thinking about the standard local weak convergence, well, these two are closely related. The way that I like to think about them is that if you were able to prove the strong one, then you'll get this one sort of as a byproduct for free. Just tweak a few little steps and you get this other mode of convergence, which tells us something about the proportion of the subgraphs that happen to have a certain property, right? So it has a nice interpretation from the point of view of the fact that this is an indicator, which is literally talking just about the proportion of seeing any particular structure on my graph. And when you have marks, we just need to tweak that definition just a bit to say that we have any fixed graph. This is undirected since we're only looking at the graph structure with set of vertices V, set of edges E. And then we're going to have any set of subsets of my mark space, whatever I want them. And all I require of them is that there are continuity points or continuity sets of the limiting distribution. So then the average, so 1 over n, the number of subgraphs started at I of depth k that happen to have the property of being isomorphic to G and having marks in the set of predetermined sets B's that I define, converges in probability to the same quantity but on the limiting graph, right? So this is the sense of local weak convergence in probability with the added feature of general marks. So now I have those definitions out of the way, then let me just go back to our preferential attachment models. So we have the graph, the sequence of graphs here, G, V, N, En, and I'm going to assume that my attachment function is linear. So here the A is either going to be a 0 or a 1, depending on what we look at. All I need to ensure is that when this is A is 0, that B is strictly positive. And if A is 1, then I can make this sort of still negative as long as everything is strictly positive. So now
just quickly, just to pick up on a question that's come up in the chat. So Oliver says, in the discrete case or without marks, are the two notions of convergence different?
Yes, they are. So there's one little step that is required extra to get the convergence in probability. That usually has to do with the covariance. So this sense over here, the strong coupling, implies this result sort of trivially if I put here a probability. Okay. So the convergence of those, that's perfectly fine, and that's a very simple argument. But once I drop the probability, then there's one tiny step that usually implies making sure that the covariance between two of these indicators is asymptotically negligible. That's the one step that's missing. But again, it's still sort of a byproduct in the sense that if you have the proof for the other part, then you'll probably just tweak it a little bit and get this one. So they're not that far apart, but there are different notions of convergence, and they do not just immediately imply each other. So now I'm going to have some conditions on the marks, and as I said, I'm thinking of some empirical sequence of the marks. And so this is my empirical measure for the marks. I define that as a measure just because this could be general valued. There are some really neat examples when these are infinite sequences. So, again, keep in mind that I will talk about here in this talk just about marks that are the out degree, but the setup works for other problems as well. And my favorite mode of convergence is whatever Wasserstein metric works for the problem. And why do I like those? Because I like heavy tails, and the Wasserstein metric gives me a lot of control of those tails at the end, and it allows for really nice tricks when we're looking at recursions. So the standard way in which I like to think of my conditions is assume that the marks have some limiting distribution in some Wasserstein sense, and this probability, because these are empirical measures, only needs to hold in probability. And again, for the rest of this, these are just integer values. Now, let me explain what the limit for these things are. And I'm sure some of you are very familiar with what the limit you think it is. I'm going to phrase it a little bit differently. So let me get to that point. So in general, I'm going to assume that I have a pure birth process here, psi, that starts at 0, that at time 0 it starts at 0, and that grows according to my function f, whatever f may be. And again, if you want to think about the general case, this f doesn't have to be linear, just needs to be sublinear, and that's fine. But I'm going to stick to the linear case here. Then I'm going to assume that there exists lambdas that's strictly positive. That is my Malthusian parameter for the process that solves this equation equal to 1. And then I'm going to take a whole bunch of IID copies of this point process, many of them. I'm going to create my out degrees this time as an IID sequence having the limiting distribution that I showed you before, independent of the point processes themselves. And now I'm going to create a new process here by taking the superposition. So for vertex n, or for element n, or individual n, because it's going to be a massive tree, then this is defined as a superposition of NIID, of dn plus IID copies of my sort of standard process. So I'm putting together lots of little copies of this guy over here. And with those, I'm going to define a continuous time branching process with fitness, because each vertex has a different initial value, right? So it starts with a different parameter, so it has fitness there. And this is going to define a continuous time branching process where each individual that is born reproduces according to this same rule, independently of anybody else. Now I'm going to put some notation. This is just too much notation. So if it's a little bit different than what you're used to, just bear in mind that I need to keep track of the marks. So I run out of space usually of where to put them. So I'm going to define this T. This is my tree. It's going to be the branching process. And I'm going to put the time down here as a subscript to define the discrete skeleton of my branching process that is run by those sigma bars. I'm going to keep the parentheses that is usually used for the time to add the mark space there. So there's too many things going on. So now this T of D plus refers to this graph that is constructed using the discrete skeleton of my branching process, where the marks are having distribution, this D plus. And if you wonder how I'm going to assign those marks, well, the way that I do is for each individual that is born to this tree, I'm going to give it a mark that is whichever an element between the sequence of out degrees. So remember, this is going to be coming from the graph, the preferential attachment graph, where each vertex comes in and is going to have a given out degree. So the one that I'm going to attach is whoever is in that particular segment of my random walk that is being defined by these out degrees that I'm sampling. So many of these births, that birth SI plus 1, SI plus 2, all the way to SI plus 1, are going to have the same mark. So the marks are the same for subsets of my births. Now I'm going to define this tau to be an exponential random variable with parameter lambda. Lambda is the Malthusian parameter of one of those copies of psi. And what we have is the main sort of coupling theorem here that says that our sequence of preferential or uniform attachment graphs or general attachment graphs for the general F case converges both in the local weak sense and probability, and admits a strong coupling, both, with the limiting object, which is the tree stopped at the random time tau with the marks d+. And you would think, well, where did that come from? Since this was a graph that had non-trivial structure and I ended up with a tree. Well, I'll get to that. The first thing that I said is, you might have seen the limit and it goes under a different name. The original proof for the case of the fixed out degree is the work by Berger, Borgs, Chase, and Saveri in 2014. And the way that they describe the limit is something called a Polya point graph. This other approach is slightly different, is completely equivalent. It just comes in a little bit more useful for many things. It's a little bit more practical to think about it that way than in terms of the Polya point graph. So they are the same, they're just different ways of looking at the same object. Now, the original statement is given only for local weak conversion probability. This construction that we have allows us to get both the strong and the local weak conversion probability at the same time. The special case of out degree exactly 1, so a tree with general F, is due to Rudas, Toth, and Valco in 2006. It's very similar to what we have here with the local weak convergence improbability as well. And there's a general case as a special case of the same ideas that I'm going to talk about for the uniform attachment graph with fixed out degree M that you can find in this paper by Garavaglia and van der Hofstede in 2017. They don't have the local weak limit, but the construction is there. So just to show you some pictures, because pictures are always nice, here's the original way in which we can construct the local limit. We start with a massive branching process that we're going to let grow for a total amount of Sn. Remember here, Sn is the sum of the di's plus up to n I equals 1. So I have many of these. To each one of those, I'm going to color them by pieces. So if the first one has an out degree of 2, I have 2 reds. The next one has out degree 3, so I have 3 greens. Then the next one has degree 1, so this one is blue, etc., etc. So I associate them with a color, and then I collapse them. So when I collapse them, now these two are the same vertex. Now the red one, you can see that there's an edge between 2 of the same class. That's this self loop right here. And then, you can see that from the pink one to the red one, there should be 1 edge. That's this one. From the green one to the red, there's 1 here and 1 there. So those are these 2, 1 and 2. So you get the idea that I can take this sort of giant lifted branching process, collapse it, and get my non-trivial graph where, as you can see, there's a lot of weird stuff going on, especially at the beginning. So how does that become a tree? Well, it becomes a tree because there's a lot of ugly things that are happening up here. Definitely not tree in any way. They look ugly, but we don't care about the tree. We care about a uniformly chosen vertex. And like anything that is growing exponentially fast, there's a lot more people here than there. So once I look a little bit down and not at the first vertex, but let's say at a uniformly chosen vertex I, I'm at the fringe of the big tree. And at the fringe, what's happening is that for any given node that, offspring that comes in, after collapsing, only one of them is in the direct lineage of any one vertex I. So structurally speaking, these other guys, these other out degrees are pointing to some other nodes that are not part of the tree. So the local weak limit is just obtained by sticking to the ones that are direct descendants of vertex I. And the proof basically goes by saying that by showing that the probability of any of these guys, mapping to somebody else in the ancestry of the 3D descendants of I is negligible in the limit. Here you can see that the last vertex that I created is vertex n. That's where I stopped the entire procedure. So this is how the local weak limit is obtained. And as I said, it's sort of nice that it has a very nice, elegant description that allows us to do interesting things. If you're looking at Indegree distribution of this graph, that's well known that the preferential attachment graph is a scale-free graph. It has heavy-tailed degrees. here we added the random out degree. So you have a play between two different types of heavy tail phenomenon. So you get an interesting limit for the Indegree. So here D minus is my limiting Indegree on the graph. This again is my the discrete skeleton of the couple tree. This I'm going to call F bar to be the tail distribution of the out degree, however I'm choosing those. Out degrees, I'm assuming, remember, I assume convergence in D1, so I get by free from what I already assumed that this has finite mean. So the out degrees have finite mean. Other than that, they can be as heavy tail as you want them to be. And in the preferential attachment case where I have attachment function x plus some constant, then what we can see is that the Indegree distribution is asymptotically these two components. This comes from standard heavy tail analysis. One comes from the, we have a representation in terms of the sum of heavy tail random variables. This is the number of random variables that we're doing. So this is a sub-exponential asymptotic, and then on average you have mu. And each of those is my point process. And the other one comes from what I call usually the maximum part of that asymptotic, which is a probability of having one of them that is very large. And that's the tail of the, of having just too many of them that are large. And that is the tail distribution of the out degree. And this expected value is equal to 1. And this one is known to be a power law with exponent 2 plus b over mu for this specific case. And you can see that we have both who wins depending on who's heavier. If they're both equally heavy, then you have those two terms, and those define together the constant. So in general, in the preferential attachment case, this is always a scale-free graph. Nothing new there, other perhaps than you get this play of two different indices if you allow the out degrees to compete. Here's the ones that's a bit more interesting because this leads to interesting behavior. So this is the uniform case where nobody's choosing according to who has already been making a lot of friends. Where in this particular case, all we're doing is superimposing Poisson processes. So it's very straightforward to see that the Indegree has a distribution of a mixed Poisson process stopped at that exponential time with rate B and mixed in with the out degree distribution. Now, what can happen? Well, let me give you two opposite ends of what can happen. The first one would be if we assume that the out degrees are all constant, in which case the distribution of the Indegree is geometric with parameter 1 over n plus 1. And the other extreme is, let's assume that the out degrees are heavy-tailed and particularly regularly varying. In that case, the Indegree distribution is also regularly varying with this particular constant right here. Here, the index that I'm assuming is alpha. I put the greater or equal than 1 just because of, the special case of alpha equal to 1 depends on the slowly varying part, whether you have finite mean or not. So the uniform attachment case can go both ways, depending on how you pick the out degree, right? It can be scale-free or it can be light-tailed. Most of the time, you would think that we stick to the light-tailed, and that's great. That's fine. So now let me talk a bit about PageRank and connect these two and why things look really weird. So PageRank is just a random walk. Now, PageRank in its origin had a different purpose. I'm not sure that the original idea of PageRank was to think about a random walk. I think historically that came in later. The whole point was to try to rank all the vertices on the web graph with a universal number so that whenever your web browser could find all the pages related to the keywords that you search, that it would be know in which order to show them. As we know, we all have about 1 page worth of patience for any one search. So it was important to show this, and the Page and Brin came up with this particular recursion for computing the ranks of pages, which is nothing but a weighted average of the ranks of the inbound neighbors plus this teleportation parameter. Now, if you think about this from a point of view of a probabilist, then this is a random walk. Now, keep in mind that if I wanted just to assign to each node on a graph its importance or its relevance, one thing I could say, well, I'll just run a random walk, compute the stationary distribution of that random walk, and say, well, by definition, the stationary distribution value for one particular vertex is just the long run proportion of time that I would go there. So if that long run proportion is big, then I should be important. If that long run proportion is small, I shouldn't. So it makes sense that the random walk gives you relevance when you're looking for centrality in networks. The problem, of course, being here that the web graph and many other interesting graphs are completely disconnected. So that's not going to work very well for us. So that's what this little thing does over here. It adds an extra coin flip that says, well, I'm going to toss a coin that lands heads with priority C. If it lands heads, I choose uniformly at random which edge to follow. If it lands tails, I'm going to pick from this other probability distribution Q. This is why I said that the Q it comes in handy to allow some dependence, because this, of course, needs to add to 1. In the limit, that makes no difference. The strong law of large number takes care of it. But in the pre-limit, you don't want to assume that they're exactly independent. Now, in terms of matrix notation, this is even simpler than what I showed before, because once you multiply everything by n, this defines something called the scale-free PageRank. This is not a scaling in the sense that we're making something that blows up or goes to 0 become sort of some other random thing. Here, it's actually literally something that's going to be well-defined regardless of, because the page ranks are going to be scaling at order 1 over n. By multiplying them by n, these stars are well-defined as n goes to infinity. So they're called the scale-free page ranks. And in this notation here, the q also gets multiplied by n. So now this is going to be some set of values that are well-defined in general. They're neither going to infinity nor going to 0. And neither are the page ranks. In matrix notation, this becomes this linear recursion, r equals some vector. I'm multiplying on the left, just like in probability. So, not in linear algebra. R times some matrix M. This matrix M is nothing but the diagonal matrix of the weights defined by the out degrees and the damping factors times the adjacency matrix of the graph. And so here's my notation to keep track, to make sure that it's always well-defined in term, even if the out degree is 0. When the out degree is 0, you have the adjacency matrix that has 0 sums. The standard thing to do in this case is you put in C times the personalization vector to fix that. So that's PageRank. And what's nice about PageRank is that it's a local quantity. And to see that this is local, well, think of that matrix M that I defined. You look at its infinity norm, that's equal to C. That C is always assumed to be strictly smaller than 1. In practice, C is equal to 0.85. And that means that we have geometrically fast convergence, right? And that means that because it's converging geometrically fast, I might as well truncate at a finite level, right? And the geometric expansion of the solution to the system of equations. And I'm perfectly fine doing this. And what's nice that I get on the right-hand side is that this becomes a local quantity. This is a function that depends only on the in component of depth k of any one vertex. So it's definitely a local computation, which means local weak limits should determine their behavior. Here is my notation for the PageRank of a randomly chosen vertex. So here IN is uniformly chosen in the vertex set. And I'm just going to look at the PageRank of that particular vertex IN as I choose it. So this is a random variable. In general, people have always looked at the asymptotic behavior of that, if this converges. In many cases, it does. Empirically, it always converges to something. And I'm going to call that something to R star. Now, without going into any math, since I started working on this almost 15 years ago, the folklore in the internet literature has always been that if I give you a scale-free graph, one that has n-degrees that are heavy-tailed, PageRank will also be heavy-tailed. And this has been one of those things that everybody sort of takes for granted. It's always true. Any graph that you give me that is scale-free or looks scale-free long enough will have the behavior that the PageRank looks scale-free. And it was sort of a puzzle for many years to try to see what does that mean that they have the same index. They're not the same. So ranking using PageRank and ranking by the n-degree do not give the same results. These are different centrality measures. However, why do they still have the same degree? And that was sort of an open question for a while. As I said, the folklore is that this is true. Nelly Liebeck and I, many years ago, we just started referring to this as the power law hypothesis. And for a long time, Nobody knew why it was true. Let me tell you what we know and when it's true. So think about not preferential attachment graphs or not general attachment graphs, but just static directed random graphs. So take your directed version of Erdős-Renyi, the Chung-Lu graph, Nora's rate-through, generalized random graph, or even the configuration model, any of those. Take its directed version. These are static graphs. Static because we're only meant to check one snapshot of our real world graph. Well, for static graphs, we know that in any of these cases, the local weak limit is a marked, delayed Galton-Watson process. The marked comes from those out degrees or personalization or whatever else we have. The delay comes from the size bias that is present in any of these models other than the Erdős-Renyi. That size bias is significant. It's something that we should never ignore because it's really, really heavy when you have a scale-free graph. Now that's a nice limit. It's a very different kind of limit than the one that I showed you before. This is an infinite tree after all, most of the times. So it has other attributes different than the ones on the preferential attachment graphs. However, for this particular family of random graphs, it is known that if we have that the typical Indegree and marks converge in some way, usually again in the Wasserstein metric of order 1, and if the limiting distribution of the Indegree happens to be heavy tail and particularly regularly varying, then indeed the power law hypothesis is true. So that was the first ever proof of these empirical observation that had been around for many, many years. And the first sort of attempt at this was work with Nelly Lidbeck and my student Ningyuan Chen back many years ago. It started with simple cases on the configuration model, but eventually evolved to the most complex case where you have dependence between Indegree and out degree. You get lots of interesting stuff going on, but in great generality for any static graph whose local weak limit is a Galton-Watson process, the power law hypothesis is good. We're good. Everything is nice as expected. So we know that holds, but we also get a little extra from those proofs, and that's that the limiting PageRank admits a very nice representation. And that representation is in terms of something we call the solutions to a stochastic fixed point equation. So in particular, these R star that happens to be the limit in the theorem that I showed you is it's a sum, or it's a random sum of a number here of, depending on the Indegree, of some independent random variables xj's, which happen to be regularly varying with index alpha, independent of these two. And these x's happen to be copies of the so-called special endogenous solution to the smoothing transform with specific parameters. I'm not going to go into the details of that, but what I want to use this for is to explain that this representation is very important to getting those heavy tails. Why? Because I'm looking at a random sum with a heavy tail number of a heavy tail IID observations. The Q usually doesn't play a role, it doesn't compete, but this is still a very, very tractable thing. The x's in particular have the same distribution as the damping factor times the PageRank of one vertex divided by its subdegree of the size bias version, because these are not the original, but known to be neighbors of somebody. This is very heavy tail. This doesn't even have finite mean sometimes. And this is also sort of special. It's not your standard out degree. And together they compensate each other. They're very, very dependent to get something that does have finite mean. More importantly, you get really nice intuition about what is going on and what the most likely way to the heavy-tailed asymptotic is, or the large rank is. And it says that vertices that are going to end up with very high PageRank are either those that have one other neighbor that is also very highly ranked, so the maximum here. So I just need one very famous vertex or one very central vertex to be pointing to me, and that would give me also a high PageRank. Or I just need to have a very large number of neighbors, right? So this is sort of, both of them have the same weight. They just sort of play two different scenarios of what the most likely path to the large deviations is. So all of the story in static graphs is very well understood. And that's what we wanted to figure out. Well, can we do that in preferential attachment graphs or in general attachment graphs? So that's what Shan and I did. And we started again back to the first model that I explained, stick to the linear case. So either preferential attachment or uniform attachment. And we started with a special case of fixed out degrees M. For the purpose of this, I'm just going to make the personalization equal to 1 for everything. This is the same local weak limit that I showed you, the same graph, and this is the R star that's going to be the PageRank computed on the root of the local weak limit. Not very surprisingly, the PageRank on the graph of a uniformly chosen vertex converges in distribution to that limit. We don't have yet the D1, but I'm pretty sure that it's true. And also in the local weak sense, right? The proportion of vertices on the graph that have a PageRank in any particular set converges to the corresponding probability distribution of the limit, assuming that I'm evaluating in a point of continuity of the limit. In this case, the limit is sort of not continuous, so that's modulus a little detail there. So let's go to the last part and sort of the best part of the story, which is those tails of PageRank. In the preferential attachment graph, we have a scale-free graph. So you expect PageRank to be scale-free, and indeed it is. The indices are the same. There are complicated functions of the parameters of my graph, but they are scale-free, right? These are power laws of an index given by this big quantity up here. And that's expected that it would be heavy tail. However, remember on the preferential attachment graph, the index, and then let me go back to that, the index of the Indegree is not that. Where was it? Did I already pass it? This is the index. This is 2 plus b over m in this case, and this is different. This is something a lot more complicated. As a matter of fact, it's a lot heavier in general. So that was weird. But then what got even weirder is take the uniform attachment graph, fixed out degree. So this is a geometric Indegree. And this is still heavy tail. Why? That's the question. So in general, PageRank on these general attachment graphs is heavy-tailed, regardless of whether your original graph is scale-free or not. And that's something new. That's something we had never seen. Moreover, these power law hypotheses that we thought was true and that computer scientists have thought to be true for a very long time, it's actually not quite true. Right? This is also serving as a counterexample of the power law hypothesis because the index of the PageRank here does not coincide with the index, which is this one over here, of the Indegree distribution. And this means that whatever is going on here is very different, qualitatively speaking, than what we see in static graphs. So this is a story of tails that we did not expect. Anybody we've talked to, nobody expected this. And as a matter of fact, nobody really expected that we would end up getting a different index for the one graph that we knew that had to be heavy-tailed, but not with a different exponent that is heavier. So PageRank is capturing something more. And this is where the interpretation of that static case sort of sheds some light into what's going on. So if we think about a configuration graph or a Chunglu graph, any of these graphs that are heavy-tailed, but that still have the nice local structure being a Galton-Watson process, where every node, with the exception of the root, is the same, right? They all are nice and they're very independent in general. So in that case, the independence is allowing us to just get those standard heavy tail asymptotics that I explained. If one vertex is going to be very highly ranked or very central to the network, it usually is because either they have a very large in degree, so it's just a function of that in degree, or because they're close to somebody else who already has a high PageRank, and that is sort of giving by closeness and by peer approval, let's call it, also importance to the other vertex. On the other hand, the fact that the local weak limit is sort of this Galton-Watson process, it tells us also that all the vertices are sort of the same. So the very large vertices that you would expect to see, they're everywhere, right? They can appear anywhere in the graph. They are not necessarily clustered in any kind of way. Now, that's exactly, in my opinion, what is going on here. When you have an evolving graph, obviously the oldest vertices tend to be very different from the younger ones. The older vertices have humongous in degrees in general. They have a lot of self-loops. They have a lot of multi-edges. They tend to be very, very different. But even as we move down to the fringe and we're looking at the typical elements of these graphs, there's still some of that lingers. So if I pick just uniformly at random somebody that is very, very close to the edge, of course, that's going to have chances of not getting too much PageRank in general, because everybody's sort of small, they won't have too many offspring. But anywhere in the middle, there's a good chance that they will accumulate something. And the fact that they're accumulating something in that they're all related to the length of the subtree that I have, and I have a picture like looks like this. Here I'm stopping here. So all of my vertices here refer to that small triangle and the height of that triangle. And that height is affecting everybody. And if that height tends to be big, it affects everybody on the inbound neighbors of a vertex. So they're very, very much correlated with each other positively, because the longer the stopping time tau, the longer the time they have to accrue PageRank or centrality in the network. And they tend to be together. Not only are they correlated among each other, but they're also correlated with the in degree. And maybe I can write something just to put this a little bit clearer. So the PageRank in this case is going to have some form like this, where I have the in degree of a vertex, and this I'm going to have all the offspring in the order of their arrival for the particular vertex, the root of the tree. And these are going to be C times the vertices of those offspring. And I'm going to put here the tau. And then I'm going to put here also the tau, because this is what's introducing dependence. And then something here, 1 minus, right? Like that. Divided here by the out degree, but if the out degree is constant, that's just one number. So that doesn't affect anything. And you can see they're all related, the in degree and all the neighbors with that length. So now these are all related to each other on I through the stopping time, through the tau. And not only are they related to each other, they're related to this. So what that's telling us is that when you have somebody that is old or oldish, they're going to tend to have higher in degrees, and they're also going to attract offsprings that are going to have enough time to develop high PageRanks. So a lot of dependencies going on. So this object right here certainly does not behave in the same way as we would have in the Galton-Watson process, but in a very different kind of heavy tail scenario, where you have a lot of dependence that is playing into each other, and you end up having large vertices, large in degree vertices, with also large PageRank vertices as its offspring. So these models are very different. It's a funny joke. I think Remco van der Hoofd once said, well, this just tells you how bad these models are for anything. I'm not sure if I agree with that statement, but whatever it is, the moral of the story is that this family of models can give you interesting surprises of knowing what the timestamp of vertices is. And it gives you really interesting things that not many people expected. That's all I have for today. So I'm happy to answer any questions now.
Thank you very much. Would anybody like to ask anything? I've also got some questions, but I'm happy to go after other people if they have. Okay, so maybe I can just start by there was something I didn't understand in the sort of technical part. How does the Malthusian parameter come up into the model? So it appears as the sort of parameter of your exponential.
Yeah.
Could you just give me a quick idea of why?
Absolutely. I have a picture. And that's actually really, really nice. So the Malthusian parameter is going to first determine the length, the amount of time that you need to grow the tree until you're able to see the Sn vertices, right? Because this is n once I collapse them, but before that, I'm really seeing Sn vertices, the sum of all the degrees up to n, right? So on one hand, it gives me the length of the total thing. But on the other one, it turns out that that particular exponential is coming from this displacement. So the way that we construct the coupling is we're looking at a uniform number between 1 and n, and it's this piece over here that gives us the exponential, and it's going to be proportional to the number of vertices that I have seen up to here. Up to here, I've seen SI vertices, and from here to here, as I said, we have SN. And when you take the ratio of those two and do the exponential that goes with the growth of the underlying big tree, you end up with 1 over lambda log of the ratio of Sn over S over Si, and that's the exponential with rate lambda, right? So it comes from this displacement, not from this one, which is sort of interesting, right? It's not really talking about this length. It's talking about this one over here, which is sort of weird.
Great.
Does that answer your question?
Yes, definitely. Oliver has a question. Go ahead. You're unmuted.
So, and the discrete, should I read it? In the discrete case, without marks are the two notions. Oh, I think
that we already dealt with, but I can't hear Oliver. I think he's trying to speak, and I think his microphone isn't on. Can you type it in the chat? Oh, there we go. He hasn't tested it. Okay. Okay. Well, perhaps I can ask another in that case. So I assume that in the case where you take more general degrees, you could expect even weirder behavior to occur. So here you fixed your out degrees to be m, if I understood correctly. Suppose you took those to be some sort of interesting random variable as well. Could you, I mean, would you anticipate getting even weirder looking tail behavior here?
Well, yes, I don't know exactly what, but yes. So right now we do not have yet approved for the random out degree for the PageRank part. Still working on that. But given that we already saw sort of weird things, and even in the Indegree, you end up getting with these mixtures of competition of tails, I could imagine that's something where it could happen. Now, based on my experience with static models, the out degree doesn't play that big of a role, right? So the static case is determined by the Indegree. So there's a chance I may be wrong, but yes, I am hoping that something really weird can happen.
Thank you very much.
Can I try again?
Yes, now we can hear you. Excellent.
Set the right microphone. In the original model case, there's some sort of branching process analysis, I think, of not just of the in-tree, but the in and out thing that works with a branching process where you have marks by basically by the time that a vertex is born, so by sort of I over n or something, which.
So here.
What I meant for the Barabashi-Albert model, when it was analyzed a bit before this, there's a different way of getting a branching process where you where the points are marked by the time that a vertex is born. And I'm not sure, is it just, it's all more specialized, it's not as general as this, but I don't know, is that somehow the same thing really? I'm not sure I really followed your tree. Is it that you effectively have the points in the tree are marked with a time as well?
Well, the vertices are order are named according to their order of arrival. And I did not mention this. Yes, the actual time of arrival plays a bit of a role in the calculations themselves.
Uh-huh.
But so those are the same. What I'm not sure what we're comparing this to in your question, but there probably are some similarities. Now, this construction in particular came from the idea of looking at a paper by Remco van der Hofstad and Alessandro Garavaglia on collapsed trees, or collapsed branching processes. Turns out that when this function is a linear function, you can just sort of superimpose the different branching processes, and it sort of does the trick to getting you the cumulative F. So that idea we took from there. So it's not ours. What is new is that the standard analysis of these models usually goes through the sort of continuous time branching process analyses, whereas our coupling is from the original graph by looking at this displacement, as I was explaining before, of first fixing I, choosing I first, and then figuring out how to estimate the length of the subtree down here. And because it's discrete, it gives you this sort of nice strong coupling in the process. So that is new. That's this piece. This length is deterministic, by the way, once I, you have I. It's nothing, as I said, than the length is 1 over lambda log of S I over Sn. So this length. So that's deterministic. Where the randomness comes actually from the top. And this way of looking at it is new and is related to the collapsing procedure, but it gives a different kind of proof.
Okay. Thank you.
Anybody else? I can't see anything else in the chat. If not, what I'm going to do is I'm going to stop the recording and then I'm going to invite everybody to unmute and give Mariana a big round of applause.